All right, so again, I have three functions up here, J, H, and K. I want to find the tangent slope generators for these. J, I can distribute and take the derivative of, no problem. H and K, H I could do, but it's going to take me forever to do so. K I can't. So I need a new rule that I can use for all three, but have to use for H and K, unless I want to take forever to distribute things, okay? And the commonality between all three is that they're compositions of two functions. There's an inside and an outside. The chain rule is the rule to take the derivatives of these compositions. This is what we do with the chain rule. We understand that there is an outside and an inside. That's my outside. This is my inside. Turns out the derivative of a composition is just equal to the product of the derivative of the individual functions that are being composed. If outside is the F and inside is the G, if I took the derivative of F of stuff and say it's F prime and the derivative of G is G prime and multiply those two together, that is going to be what I want. The only problem is we have some blank stuff here. We're just going to have to fill in whatever started out inside of F when we have the derivative of it. Okay? So derivative of a composition is equal to the product of the derivative of the composed functions. Composed functions. There is that product. Now let's go ahead and do the previous three using this new rule, where the first one, J, we'll be able to check to make sure I can get the correct derivative. Because I did already take the derivative of J by distributing, but let's pretend like I didn't want to distribute. The first thing we do for all of these compositions is understand what is the outer and inner function. I'll write O and I for outside and inside. And for J, I would consider the parentheses squared being the outside function. That's like the F of. The inside would be 2x squared plus 3. That's the G of x. Then I'm going to use arrows to designate that I'm taking the derivative. I won't write the ddx moving forward. Okay, now the derivative of 2x squared plus 3, you know what that is. You can write that down. That's 4x plus 0. But instinctually, discuss with your neighbor, what do you think we would write the derivative of parentheses squared as? If you think this is like an x squared, you'd say the derivative of x squared is 2x. Well, we're going to say the derivative of parentheses squared is 2 parentheses. So that's correct. So instinctually, we got it right. Doesn't happen often in this class. Okay, now I'm ready to write the derivative of J down because the derivative using the chain rule is just the product of the derivatives of the individual functions that are being composed. This is 2 parentheses times 4x. But we're not going to leave a derivative with just some blank space, okay? It's derivative of the outside, leave the inside alone, times the derivative of the inside. That means, like, we have to understand that 2x squared plus 3 started inside the parentheses being squared. So we are going to place that back in there. And now I can stop here. This is fine. This is the derivative. It's a tangent slope generator. If I were to simplify the 2 and the 4x to get 8x times 2x squared plus 3, great, we could do that. And I would stop there. This is like a factored form of a derivative. But just for demonstration purposes, and this is only for demonstration purposes because we already found the derivative of j by distributing and then taking the derivative. We get 16x cubed plus 24x after I squared things. Well, if I distributed the 8x, I'd get 16x cubed plus 24x, which is exactly what I saw. So here is an alternate approach to finding the derivative of j without having to distribute. Okay? But for h and k, we're going to have to use this rule because I don't have like a long time to take this to the 5th power and because I can't simplify this. So what are we going to do? Understand what is the outside and what is the inside. Write the derivatives of both. Multiply your derivatives of both of those together, and that is the correct derivative of h, so long as you know what starts on the inside of the outside. So go ahead and do that. The only thing that is missing is the blank space. Well, it's whatever started inside the outside. It's f prime of g of x, so it's like what started in the outer piece? That, or that. That needs to go inside the derivative of the outside. Okay? Would I simplify this at all? No, I'm done. If anything, you can distribute the 5 into the stuff on the right. You can't distribute it into the stuff being taken to the 4th power, but I'm not going to want to do that. So, we're done. Let's go ahead and do k and find k prime. We would simplify this a little bit. 20 times a half is 10. I have 10x cubed over root 5x to the 4th plus 3. All right, do the next one. That's on your paper. Check your answer with a neighbor. Should be pretty straightforward, right? Not that bad, as long as we utilize this rule. Now again, these rules, they come from our magical limit as h approaches 0 of f of x plus h minus f of x over h formula. Okay, if you want to see how we can arrive at this, you can look either in your book or online for the proof to see where this formula comes from. After doing this enough times, I'm not expecting you guys to be able to do this yet, but after doing this for enough times, you will be able to go directly to your answer. Oops. Which is that. And then maybe distribute the 3 into the 6x minus 2. Okay? Where does that come from? An outside, which is the stuff cubed, an inside, which is the 3x squared minus 2x plus 1, derivative 3 stuff squared, derivative 6x minus 2. Product of decomposed functions. Let's look at this guy. Sometimes we get caught up in this chain rule and we think we can use the chain rule for everything, but it might not be the right thing to do. I can. I'll show you how I could. However, I'll show you what I would rather do besides going straight to the chain rule. What I would first notice is that we have a function times another function, which means I need to utilize the product rule. However, when I'm using the product rule and I take the derivative of the second piece, that is when I need to use the chain rule. So let's see what this would look like. The derivative of the first times the second plus the derivative of the second, I'm just going to leave some space. I'll get back to that. Times the first. Let's go ahead and now find the derivative of the second piece. It's got an outside, it's got an inside. The outside is the fourth power. The inside is the 2x cubed minus 3. And take the derivative of the outside and the inside and find the product of those. Fill that into the space. Go. Okay, now, probably would simplify this, at least the right side, I can simplify. I can't put this 2x into the 2x cubed minus 3 to the fourth. But I can multiply the 4 and the 6x squared and the x squared together to get me 24x to the fourth. Okay? And that looks like my simplified answer. And write that down. Look for the answer on a multiple choice question, and I don't see this anywhere, which means I need to simplify more. And I look at my multiple choice answers, and I see that they don't want me to distribute everything. Instead, they want me to get answers that are products, like this times this times this, or something like that. Which means I need to take this, which is a sum of two different terms, and turn it into a product of multiple terms. Gosh, how am I going to do that? Well, if I asked you to turn this sum into a product, you would know what to do. Discuss with your neighbors. What would you do to turn this sum into a product? If you say factor out of 2x, good. If you factor out of 2x, you turn a sum into a product. Now, there is a sum inside my term, but this is a product. This term times this term instead of this term plus this term. So, discuss with your neighbors what can be factored out of these two terms. I can definitely take out a 2x in both of those, right? So at least I can take out a 2x. However, is there anything else that these two terms share? The 2x cubed minus 3. This has 4 of them, and this has 3 of them. I could decide to take out 3 of these 2x minus 3's. So let's see, if I take out 2x cubed minus 3 cubed. Now, what I did over here with this 2x squared plus 4x, I kind of divide out the 2x, and this is what's left over after you divide them out, factor them out. You guys should be able to see what should go here and what should go here. Let's see if you can figure out the correct stuff that goes there and there. Check with your neighbor. We only have the 2x is gone, it's divided out. 3 of the 4 of them are divided out, which means I just have 1 of these left over. If you want to put a 1 here, fine, whatever, doesn't matter. For the second one, all of the 2x cubed minus 3's are gone. I divide 24x to the fourth by 2x, I get 12x cubed. Now, we will be able to see this as an answer on a multiple choice question. Sometimes when you have multiple rules, we will be forced to simplify more than we may be comfortable with. But this is secondary. This is a secondary kind of thing, this simplification. The main part of what we did is right here, where we use the product rule, and within the product rule, we use the chain rule. This is just simplify. Okay? Now, to the right, it looks like we have a little bit of space. I'd like you to take the derivative of this. This is another example of a problem that will have multiple rules going on. So for the previous one, we started by using the product rule, and then within the product rule, we had to use the chain rule to take the derivative of the 2x cubed minus 3 to the fourth. This one, we have to start with the chain rule. And then within the chain, we need to use the quotient rule. I take a product of the derivatives of my individual pieces. The first one using the power rule, 3 stuff squared. The second one using the quotient rule. Yep.
What if it's 2 via 3, like the power, like in the, would it be 3 or,
yeah, it would be. Like in the bottom one, the final answer should be a 2 instead of a 3 on the first one, the top one, the power for other parentheses.
Oh, yeah. Good, Mr. Diaz. Ladies over there, keep your phones away. Thank you. Okay, now, I don't see that as an answer. I need to simplify. What can be done to simplify? This could be written as x squared over x minus 1 squared. We could square the top and the bottom. What can be done now? negative 3x squared over x minus 1 to the fourth. Okay, so when we use multiple rules, we might have to simplify. If you're squaring a fraction, you have to square the top and the bottom. So I squared the top and the bottom, and then boom, those can be combined. Okay? All right. Other compositions occur with trig functions. We have two different types of compositions. I have sine squared of x and the sine of x squared. The key to the difference of these two is how you would write them with parentheses. We should know by now that the sine squared of x can be written as the sine of x quantity squared. Whereas the sine of x squared would be written as the sine of x squared. Now, if I were to take the derivatives of both of these, we would need to understand how the outsides and the insides differ. For the guy on the left, the outside is what we've kind of been used to so far. It's the stuff being squared. Whereas the inside is the sine function. The guy on the right, what is the outside? Sine of stuff. What is the inside? The x squared. Okay. Now, the one on the left, let's find the derivative of it. We're used to this from the limited examples we've done. We have 2 times stuff, and then I'd write the derivative of sine just as the derivative of sine cosine. So I got 2 times stuff times cos x. What's the stuff? That's sine x. Can we put our phones all the way away, please? Thank you. The guy on the right, what would we say is the derivative of sine of stuff? Cosine of stuff is correct. Derivative of x squared to x. Let's see how the derivative is going to be different in this case. We got some space, okay. Right below these, on the same page, find y prime if y is x cos x squared. And I want to see how many of you are going to make the mistake I think you're going to make. If we go straight to the chain rule, we say the outside is x cos of, guess what? That's a product. Now, you could take the derivative of that outside using the product rule, but most people won't. So instead, make sure you recognize that this is a product. Many of you, I am certain, made that mistake. Derivative of the first times the second plus the derivative of the second times the first. I left some blank space for the derivative of the second piece. For the derivative of the second piece, you need to understand cosine's the outside, x squared is the inside. The derivative of cosine is negative sine. The derivative of x squared is 2x. Take the product of the derivatives of the individual pieces being composed. Sorry. Okay, and if I were to simplify, I would probably just write the guy on the right as minus 2x squared sine x squared. All right, let's go to the next couple. I'd like you to change the one on the right to be secant of x to the fifth. Okay, go ahead and write down the outsides and the insides for both of these. Make sure you change that one on the right to secant x to the fifth. There's a reason why I want to use secant in both of these situations. Sorry. Reset, go. What's the outside? What's the inside? What is the derivatives? The one on the left is a little bit misleading because the parentheses are around the x, but you know, we should see that the cubed is on the outside. So I wouldn't write the outside as secant cubed. I'd write the outside as stuff cubed. Inside is the secant of x. Easy simplification there. Let's take that secant squared, multiply by the other secant. We have secant cubed x tan x. For the one on the right, the reason why I use secant again is because in this case it is the outside. Secant of stuff, where the inside is the x to the fifth. Now, a lot of times, using the chain rule with something like a secant, whose derivative is multiple terms, students make mistakes. They either write the derivative as secant tangent of stuff. This would be wrong. They sometimes write secant x tan of stuff. That would be wrong. It is the secant of stuff times the tangent of stuff. Just pretend like the stuff is an x. Derivative of secant x is secant x times tangent x. So I need blanks in both locations, and I'm going to have to fill in both blanks.
On the left column,
Yep.
would you have to simplify it all the way down?
Probably you would on a multiple choice question.
Okay, so if you want to that on the
That's fine. Yep. But let's keep in mind that the test is around the corner. Okay, would not simplify the one on the right. All right, if you feel comfortable so far, great. It gets trickier. This next one, f of t, I could write as the sine of 4t squared cubed. Now there's two ways I can do this. I prefer the second way, but I'll show you both. Actually, I prefer the first way, but I'll show you both, because usually whichever thing I say first, students just grab onto that and they do that. I prefer the first way. The first way is to understand that this is a composition of three functions. You were saying? I know. Where we have an outside, a middle, and an inside. Well, if when we have a composition, the derivative is just a product of the composed functions, the derivative of the composed functions, well then, if I can just take the derivative of all of these pieces and multiply them together, I will have the correct derivative. Or, let's say I'm only comfortable with outsides and insides and I'm not used to recognizing the fact that I have a middle. This is the other way, which I don't prefer. You could say, okay, the outside is the stuff cubed. The inside is the sine of 4t squared. You'd say, okay, the derivative of the outside, 3 stuff squared. But for the derivative of the inside, I have an outside and inside of that. The outside is the sine, and the inside is the 4t squared. The derivative of the outside, cosine, the derivative of the inside, 8t. And then say, okay, I need to multiply this by this derivative, which ends up being that. Okay, so understanding that the inside is a composition, you can then take its derivative by identifying its outside and inside. It's just doing the chain rule in steps and layers, where this does it all at once. Regardless, you should get the same answer. 3 stuff squared times cosine stuff times 8t. It's a little trickier figuring out what goes in the blanks, but it's all about what starts in that derivative. So what started in the cubed, it was all the sine 4t squared. What started in the sine, the 4t squared. And see if you guys can tackle the one on the right. This is 4. If you did this in a layered approach, you probably would have seen it as you were writing it down. If you wrote the middle as sine, and then the inside is 3x plus 2 to the 5th, you would have figured out as you were doing 3x plus 2 to the 5th that you'd have to use a chain rule for the derivative of 3x plus 2 to the 5th. So it doesn't matter if you wrote it down as all 4, as long as you just wrote it out, just when you got here, you'd have been like, oh, I have to use a chain rule for this. I have to do an outside and an inside. Yes.
Do you not take the 1 foot out and use it on the derivative?
The 1/4 can just stay out to the side, and you can worry about it at the end.
My outside was like sine stuff squared. I didn't.
So
I took like the 1 foot like how much the product portion was like take like the 1/3 or whatever like out and then use it later.
yes, I don't need the 1/4 here.
Okay.
I could have just wrote 1/4 down here, and then have all the derivative stuff in there.
Okay, that's
Yes, that's totally fine. It's a constant times a function. You can think of the constant 1/4, not being involved. Okay, so let's just pretend I did it like this. Well, because I'm sure we wrote it down like that. 1/4 times the 2 is 1/2. Now you'd have a 1/4, and then the 2 would be coming in there. Then cosine. Then I have to understand this has an outside and an inside. The outside is the stuff to the 5th. The inside is the 3x plus 2. That means I need a 5 stuffed to the 4th times 3. Okay, so it's really 4 different functions being composed. Multiply their derivatives. Pretty tricky, huh? On a quiz or a test, you typically only see something with 3 functions being composed. I've never seen something on an AP exam with 4 functions composed like this one. This is just like a challenge problem. Okay, but I have seen 3 multiple times. That's the final answer. Probably, if anything, I would multiply the 3 and the 5 and the 1/2 to get 15 over 2. Sine of 3x plus 2 to the 5th, cosine 3x plus 2 to the 5th. Okay? Great. Well, before we get to the table problems, how much time do we have left? Not enough time. Okay, let's get to the table problems. Okay? Tell me, what's the derivative of f of g of x? Write it down, check with your neighbor. What's the derivative of f parentheses g of x? Don't use the product rule. It's not a product. It's not f of x times g of x. It is an inside and an outside. This is the actual rule that I first introduced to you, where the outside is the f and the inside is the g of x. This is not a product. This is a composition. The derivative of the outside is f prime of the derivative of the inside is g prime of x, which means this derivative is f prime of times g prime of x. Oh, what's the inside? G of x. It's not a product. It is a composition. Now, don't go yet because I need to do the next example as well. Work inside and out. It's f prime of g of 2 times g prime of 2. Hold on. We need to find g of 2, which is 3, multiply it by g prime of 2. Notice how I went to g of 2. Now that means I need to find f prime of 3. So I have 4 times negative 2, I get negative 8. Hold on. Hold on. Hold on. The video is going to be the rest of me going through these notes because I'm using this as the video. This guy. Everybody thinks the derivative of this guy is 3 g of x squared. And it's not it. Times what? Times g prime is correct because this is a composition of stuff cubed and g of x on the inside. I will finish the remainder of these notes and we'll be posting this video online. When x is 2, g of 2 is 3, g prime of 2 is negative 2. 9 times 3, 27 times negative 2, negative 54. Finishing off, let's find the derivatives of these guys using a graph. All right, so 3 more. We'll start with this one. Derivative of f of g of x. Again, it's not a product, it's a composition. The derivative of the outside, the derivative of the inside, which means this derivative is f prime of times g prime of x. What is it? F prime of g of x. Now, to do this, I have f prime of g of 1 times g prime of 1. G prime of 1 I can find. G prime of 1 is the slope that's negative 1/2. Now, to do this piece, I need to work inside out. It's not f prime of 1, it's f prime of g of 1. G of 1 is 4. So this turns into f prime of 4. F prime of 4 is negative 1. So my answer should be positive 1/2. The next guy is a composition. I'm going to make it even tougher. What if I put a 2 here? We have a composition of not just one, but not just 2, but 3 different functions. In this one, we have an outside of the 1/2 power. The inside, I could say, is f of 2x, but you should be able to tell that this has an outside and an inside. Derivative of the outside, 1/2 stuff to the negative 1/2. The derivative of the inside, f prime of, derivative of the innermost piece, 2. So I end up with the following as my derivative. 1/2 stuff to the negative 1/2 times f prime of stuff times 2, fill in the stuff. If I plug in 4, I have 1/2 f of 8 to the negative 1/2 times f prime of 8 times 2. F of 8 is 6. F prime of 8 is 2. So this is 2's cancel, which is nice. 2 over root 6. Final example, and then I'll do some more after class. Okay. G of x cubed minus 2x plus 3, the derivative would be 3 stuff squared times g prime of stuff minus 2. Because this has an outside and an inside. When x is 4, I'd have 3 times g of 4. G of 4 is 3. G prime of 4 is 0, minus 2. That's fantastic, so that's just minus 2. But we should be able to get those values. I will finish off the notes in a second.